In this video, I'm going to be talking about some results that follow directly from the multivariable chain rule, which I went through in the last video. And so the first one that I want to talk about is some stuff about the directional derivative. Why does that formula where we just dot the gradient with the unit vector in the direction we're interested in to get the directional derivative, why does that work? And so that's what I'm going to start with. So first, I'm going to remind you of the definition of the directional derivative that we took. Okay. So we took the definition to be, let me just make sure I'm writing this correctly. Okay, the derivative of f in the direction of v was equal to, and provided that v had some sort of basically unit circle type angle, some theta, was equal to the limit as t approached 0 of f of x plus t cosine theta and y plus t sine theta minus f of x and y all divided by t. So this is the definition of the directional derivative, and I'm going to hopefully show you that that it's something that we can compute by taking the gradient and dot producting it with the unit vector in the direction we're interested in. Okay. So the first one I want to show you is going to be actually this other formula, which I think you should be able to see is pretty equivalent to what you would get after you do that dot product I'm talking about. So the theorem I want to prove for you here is that the directional derivative of f in the direction of v at a point x and y is equal to fx at x and y, partial derivative of f with respect to x at the point multiplied by cosine theta plus the directional derivative, the partial derivative with respect to y evaluated at point x, y, multiplied by sine theta. Okay, so I'm going to start by, supposing that the function f and y is differentiable, right? We're going to need that in order to apply the chain rule, which of course this is results following from the chain rule, so, I'm hoping to apply this. Okay, so I'm going to let x equal, just write it out, x equal x0 plus t cosine theta, and y equal y0 plus t sine theta. I drew the picture in the last video about why I would be interested in x0 plus t cosine theta and y0 plus t sine theta. This is basically just x being along some line in some direction. The x and y being along some line in some direction. And I think, I'm going to point out that this is a function of t, x of t and y of t. And that x prime of t is going to be cosine theta, because cosine theta is just a number. Okay? And y prime of t is going to be just sine theta. And I'm going to need that. Here in a couple of minutes. Okay. So what was I going to say here? Okay. Now the key thing is I'm going to say let g of t equal f of x and y. And maybe I'll write it as f of x of t and y of t. Okay. This is the type of thing that we can take the derivative of now using the chain rule, right? We can take g prime of t. And so g prime of t will be equal to the partial derivative of f with respect to x x of t, y of t, which I'm going to just condense to x and y, multiplied by x prime of t, plus fy times dy dt. But I know what x prime of t and y prime of t are. I just set them up there. X prime of t is cosine theta and y prime of t is sine theta. So what I'm going to do is I'm going to actually just make that substitution right now. Okay. And then I'm going to ask you to notice that when t is equal to 0, x is equal to x naught and y is equal to y naught, meaning that g prime of 0 is going to be equal to fx at x naught y naught times cosine theta plus fy at x naught y naught. Hold on a second, I got something going on back there. Yeah, I'm not sure what that was. I had some kind of situation going on in my Google Meet. It's audio feedback. I'm not even sure. I'm not even standing over there. I'm not sure how that happened, but all right. So where was I? Okay, I am over here saying that when t is equal to 0, I'm going to end up with x and y equaling x0 and y0. Okay, but also, just kind of like from the definition of a derivative from last year, I'll grab a different color before I go into this. Let's see. I've got g prime of 0 equaling, just the limit definition of the derivative, the limit of rise over run on g. The limit is t approaches 0 of g of t minus g of 0 divided by t. And it's the definition of the derivative. Now, think about what is actually g of t. G of t is f of x of t and y of t. G of t is f of x naught plus t cosine theta and y naught plus t sine theta. Okay. G of 0, G of 0 is going to be f of x naught and y naught, right? When t is 0. Okay. So, kind of like, maybe I'll kind of squeeze in over here. So yeah, since g prime of 0 is equal to this, and it's also equal to that, I'm going to have the equality that sets this thing equal to, and then I'm going to substitute on g of t, and I'm going to actually just kind of start writing in. G of t is f of x of t and y of t, which is, y0 plus t sine theta. I'm a little worried I'm about to go off my shot. No, okay, I'm just writing a little small though. G of 0 is equal to f of x naught and y naught, because t is 0. Let's see. Still in the show, just barely. All right, that's as far right as I can go. All divided by t. Okay. Now, this should look familiar, right? This is the definition of the directional derivative. Okay. Meaning that if on the right side I have the directional derivative of f in the direction of v, well, this is fx cosine theta plus fy sine theta. Which is what I'd set out to show in the first place. All right, now we're ready. We can look at the corollary, which is that the derivative of f in the direction of v is going to be, I suppose at a point x and y is going to be the gradient of f at x and y dotted with, the unit vector in the direction of v. Okay, well, I think that, the first thing is like, okay, the unit vector in the direction of v, how can we express that in terms of theta? And I don't think it should be too much for me to, propose that over here, I'm just going to assume with no loss of generality that my vector I'm interested in is in the first quadrant, and say, maybe I'll just grab a color here, like potentially pink, and say I've got a vector. And we'll call it v. And specifically, like I think you know where this is headed. That's going to be an angle theta. And then, suppose that we have some kind of, notion of 1, right? We're looking for a unit vector. So say we've got the unit circle there. It's not a terrible unit circle. So if we were to, shrink this down to a unit vector in the direction of v, what I would have would be this one here. Okay. And its components will necessarily be, well, if this is 1, then, it'll be cosine theta and sine theta. So this is why, I'm going to use this, over the course of this proof, I think, that v divided by the length of v is equal to, well, cosine theta sine theta. Okay, and that's what I'll be using to show this identity here. All right, so the gradient of f at x and y is equal to the partial derivative of f with respect to x and the partial derivative with respect to y. Over there, I've got the unit vector in the direction of v equaling cosine theta sine theta. So, based on the way the dot product works, it's going to be fx cosine theta plus fy sine theta, which I just showed is equal to the directional derivative. Okay, so this is why that formula works, where we take the gradient and we dot it with the unit vector in the direction that we're interested in to get the directional derivative. Okay, and then now I'm going to tell you a couple of things about the gradient. Okay, I'm going to tell you about the fact that if the gradient is 0, then the directional derivative is always 0 for any direction. I'm going to say that the gradient points towards the direction of greatest increase in the function, and the maximum possible value of the directional derivative is the length of the gradient. And finally, I will tell you that the gradient is going to be normal to any sort of level curve or level set in a higher dimension. Okay, so I'm going to clear off the board and I'll tell you some more stuff. All right, the first one's really easy. It's something that should sound pretty obvious, and then the proof is going to be pretty obvious too. If the gradient is 0, then the directional derivative is going to be 0 in any direction. Okay, well, I'm saying, suppose the gradient is equal to 0. Okay, well, that means that, gradient f is equal to 0, 0. And then, well, the directional derivative of f in the direction of v is going to be given by the dot product of the gradient and the unit vector in the direction of v. Okay, so it's gradient f dotted with the unit vector in the direction of v. And I erased it, but it was like right down here, and I just showed you why the unit vector in the direction of v is given by cosine theta sine theta. But moreover, I just said that the gradient of f was the 0 vector, so I'm going to just, and so it'd be 0 cosine theta plus 0 sine theta, which is going to be 0. For regardless of your choice of v, which would give you, some theta. All right, so that's the first one. Now, let me see how they said this, kind of stated this in the textbook. Because I can say it casually, but I kind of want to, be specific when I'm going to write this down for you on the video. All right, I'm right over here. So they're saying the direction of maximum increase of f is given by gradient f. The direction of maximal increase of f is gradient f. At a given point x and y. And then moreover, the maximum possible value of the directional derivative is going to be, it's going to be the length of the gradient. Okay. So I'm going to kind of just jump in, and I'm going to get to a point where I can show you that both of these things are true. So what I'm going to do is I'm going to say, okay, first of all, when I'm talking about theta, I mean the kind of the angle in the pre-calculus sense of v. So I'm interested in, I've got a gradient vector in my domain. And I've also got some other unit vector that I'm interested in taking the directional derivative in that direction. Also a two-dimensional vector. Let them have an angle between them of phi instead of theta. I know that the directional derivative of f in the direction of v is going to be given by that dot product. I just proved to you that that's valid, so I'm going to say that's equal to gradient f dotted with the unit vector in the direction of v. It's v divided by length. Okay, then I'm going to use the cosine property of the dot product from linear algebra. And if you are not in my linear algebra class, this is a fact that is true and that I probably proved in linear algebra using the law of cosines, I believe. So, and then this is going to be equal to the length of the gradient times the length of v divided by the length of v, which we'll get to in a second, times the cosine of the angle in between them. Well, the angle in between them is going to be that phi that I defined earlier. Okay. Now, v divided by length of v is necessarily a unit vector. And what makes it a unit vector is that its length is 1. Okay. So I can rewrite this and say that it's equal to the length of the gradient multiplied by the cosine of the angle between them. Now, I also know, kind of like a fact from trigonometry class, was that the maximum possible value of cosine of phi for any phi is going to be 1. Okay, and now that means that the maximum possible value of the directional derivative is just the length of the gradient multiplied by 1, which was this thing that I tried to show you, the second thing. Now, the direction of maximum increase, okay, the direction that maximizes the directional derivative is going to happen where we get that maximum value, right? And we also know that from here, cosine of phi is equal to 1 only when phi is equal to 0. And that means that, just to talk about, two vectors that have an angle of 0 between them, they're headed in the same direction. Okay? So that means that if v is in the direction of gradient f, then that's the direction of maximal increase, which is what I had set out to show in the first place. The direction of maximum increase of f is in the direction of the gradient, okay? Which is where there's an angle of 0 between the vector we're going in the direction of and the gradient. Okay, now the last thing I'm going to show you is that the gradient vector is going to be orthogonal, normal, perpendicular, whatever word you use for it, to any sort of level set. And this won't take very long. And this one is one that just like follows directly from the chain rule. All right, so if f is differentiable at x naught, y naught. I think I also want to make a remark that f of x naught, y naught is equal to c. I don't know if I need that spot in a second, but yeah, because I'm going to talk about the level curve f equals c. If f is differentiable at x naught, y naught, and the gradient is not 0, so if the gradient is not the 0 vector, then, because if it's the 0 vector, then it can't really be orthogonal to anything because it doesn't even really exist, right? So, what was I saying? Then gradient f is orthogonal to level curve f equals c. And the level curve f equals c. Oh, just enough. Okay, and how am I going to do this? All right, so really what we need is we're going to need to, get some sort of expression for this level curve. And I thought that I was maybe going to, I'm going to take a step back and talk about how am I going to actually show this, right? This is not, like, when I started thinking about this, like, how would I show that it's orthogonal, like, show two things are orthogonal by showing their dot product is 0. I know that. But what do I need to dot to 0 with a gradient? Okay. So let's just talk about, level curves. I'll make a little contour map, and I am assuming z equals f of x and y in this case. This is true for higher degrees, but it'll be much easier for me to draw z equals f of x and y. Okay, contour map. And I'm just going to only draw a couple of contours, but, say that's f of x and y equals c. I'm pretty sure you can see, you can see that's in blue. And what I need is for the gradient at the point I'm interested in, for it to run orthogonal to the level curve, that's gradient f. If that's going to be orthogonal, really what it's orthogonal to is a line tangent to the curve. Okay, so I am hoping to show that, where's my pink? I am want to show that gradient f is orthogonal to a tangent line. to that level curve. Okay, and I will be able to do that. That's not going to be very difficult. Okay, so we're going to consider the level curve, maybe just the level set f is equal to c. Maybe I can just, my proof could be maybe general, and let me look. Yeah, okay, I think that I could just, parameterize this curve or we could parameterize this surface or some sort of other object in a higher space with a parameterization. Parameterize the curve r of t equals x of t and y of t. Then, yes, now we're going to let g of t, which is kind of how all of these have gone, right? I'm going to start, passing into a kind of a single variable looking function. Let g of t equal f of r of t, right? And that's equal to c, right? That's the whole idea, is that the curve defined by r of t is all of these places where f is equal to c. And I'm supposed to write that in. So I'll just actually write that there. F equals c. And then this is also the trace of r of t. And I'm not necessarily saying that this has to be like a closed loop or anything. Sometimes for these contour maps they are. Okay, so I've got this, and I can also say that g of t is f of x of t and y of t, which is constantly equal to c. So when I take the derivative of g using the chain rule, I should get 0, right? Because the derivative of c, derivative of number, is going to be 0. So g prime of t is going to be, use the chain rule, fx times x prime of t plus fy dy dt, and that's going to be equal to 0. And then notice that this is, okay, so you'd have to use like a higher order chain rule for this, but it's good at that. Actual mechanics are going to be the same because you're going to run it through, kind of like the level curve equation, take the derivative of both sides using the chain rule. You'll see that it's 0. Oh, look, that's a dot product. It's pretty much what we're doing here, right? This is equal to fx, fy dotted with dx dt, dy dt. And notice that this is the derivative of r of t. This is r prime of t, okay? And r prime of t is a vector that is tangent to the path of r of t. That was something we saw in the previous unit. So, maybe, yeah. So if I've got r prime of t here, one of these directions, and I just showed that it dotted to 0, then I've shown that the gradient is orthogonal to that tangent, to the level curve. And I believe that that is all of the things that I had set out to show you that follow from the chain rule. This is kind of a set of things that, in the past I would have mentioned with no proof, but now that I've got some extra time, I'm going to, go in, and if you're interested, this is why all these things are true. This won't really help you solve any of the problems in my class, but it will help you gain an understanding of why, some of these claims I make are founded.